Yeah, I'm going to speak about Mars, about some results from the NOMAD instruments, and specifically about carbon dioxide density and temperature. So a few presentations before, Ariana already explained you some backgrounds about Mars. I'm going just to give a bit more details about what we need for the next slides. So here you have some temperature profiles which are in situ from landers. And this gives you, in fact, the different regions of the atmosphere. So here we do not have stratosphere, so you know that there is ozone in the atmosphere of Mars, but there is not enough ozone to have this stratosphere as we see on Earth. So here we have a separation in three different regions. So you have the troposphere going from 0 till 50 kilometer. You have the mesosphere from 50 till 100, and you have the thermosphere starting at 100 kilometer. The troposphere is the most studied region on Mars by far. There are also a lot of studies that have been done, specifically, in fact, recently with the MAVEN mission about the thermosphere, and here I'm going to speak more specifically about the mesosphere, which was less studied. So first about the NOMAD instrument. So here, so sorry it didn't work with the PowerPoint, but so NOMAD is one of the instruments on TGO. TGO is on a circular orbit at 400 kilometers. We have a 2-hour period. NOMAD has 3 channels. Ariana has shown some results with UVs. I'm going to show some results with NOMAD SO, which is an infrared spectrometer. And more specifically about NOMAD SO, the main optical components of NOMAD SO are those ones. So there is the slit defining the ILS. There is an echelle grating, which makes that most of the light is diffracted into, in this case, high diffraction orders because we have a high blaze angle. Diffraction orders, in fact, are extending from 110 till 210. The spectral range is extending from 4 micrometer to 2 micrometer, and one diffraction order is around 20 to 35 centimeter minus 1. So on the left, you have, on the right, sorry, you have some representation. So here is the theoretical, our forward model for the blaze function. So those are the diffraction orders. Here for diffraction order 161 till 168. All those diffraction orders are exactly on the same position on the detector, so we have to select one of those. So and we do this with the acousto-optic tunable filter, which is in fact this device on the left. So you have a crystal with a transducer on the side. We apply a frequency of pressure, and then we can in fact fine-tune this function along the wave numbers and select one specific diffraction order. During an occultation, SO scans up to 6 diffraction orders, and in fact there are some diffraction orders that are specific for water, for some for CO. In fact, you have water in most of the spectral range of NOMAD SO, but there are some that are better because the water lines are less sensitive to temperature. And so here what you see in blue are the lines for water, in orange are the lines for CO2, and in green, in fact, you can see them here, is some lines for carbon monoxide. And also we have different diffraction orders, which are in fact for different altitude regions. So we are using diffraction order 132. In fact, it's those very faint CO2 lines here. This is for the used for the troposphere. Then you have diffraction order 148, which is here. So those ones are used for the mesosphere. So that's the one I will be mostly using for this presentation. And you have the strong CO2 lines at 2.7 micrometers, and those ones are used for the scanning the thermosphere. So here, sorry again. Maybe I switched to the PDF or No, it will be fine. Okay. Here you have some raw spectra as provided by Nomadeso. It's here. It's already calibrated in wave number, and we are converting those in transmittances. So this was already explained before. So we use exo-atmospheric spectra to do this. What we do also is to use a linear regression. So what you see here is altitude as function of signal, and we use a simple linear regression to extrapolate the signal in the sun to avoid, in fact, any faint limb darkening that might be happening during an occultation. We are also using a criterion which is, in fact, on the selection of the sun spectra. And this is to avoid this kind of case, where, in fact, this was at the very beginning of the mission. What was happening is that there was a movement here of the eye gain antenna. And this was, in fact, changing the pointing of the spacecraft. And well, if you took this into account for considering the sun reference spectrum, well, you would get transmittant spectra that are very far away from one at the top of the atmosphere, and this is a problem if you want to retrieve aerosols. So here is an explanation of why we are using different diffraction orders. So there is obviously a highest altitude, so when the lines start to be enough thick, optically thick to be seen. And there is also a lower bound, which here for diffraction order 148 corresponds to 60 kilometers. So here what you see actually are different curves for the equivalent width, so that's the area of the line as function of tangent altitude. So tangent altitude are a function of the logarithm of the density. And the equivalent width should be a function of the logarithm of the density, and it should be linear. In this place, well, what is happening at 60 kilometers is that you have a saturation of the lines. And so when you have saturation, in fact, the line is almost no more increasing when you have a substantial increase of the density. So in fact, retrieving any density value when the lines are saturated is practically, in practice, very difficult, and we do not do that. What we do is that we use another diffraction order, where you have less intense line, and we combine those two, the retrieved density from those two profiles to get a full profile from around 10 kilometer till 100 kilometer. We cannot go lower than 10 kilometers because there is always some amount of dust that, in fact, do not let the infrared signal pass through below 10 kilometers. For the retrieval of CO2, so here we do it in several steps. So this is, in fact, similar to what we have seen for GOMOS. So here we have first a spectral inversion, so we invert the transmittant spectra into slant column, and this is done with the Azimuth program, which is a full line-by-line radiative transfer code. And for the initial temperature and pressure, we use the GEM-MARS GCM. In a second step, we in fact convert those slant column into density using the Hubble transform or the inverse of the Hubble transform, and we use a regularization which is the iterated Tikhonov method, and we fine-tune this regularization with the expected error estimation. There will be a slide about this just after this one. And once we have the local density, then we can convert this into pressure with the hydrostatic equilibrium equation. And once we have the density and the pressure, we use the ideal gas law to get the temperature. And in fact, the lines of CO2, in this case, are sensitive to pressure and temperature. So we are feeding this back to the first step. And it usually takes between 1 and 5 iterations to get a convert profile. Now about the regularization. So here you have, for the notation, here you have the slant column, which is a function of the Hubble transform applied to the density, but what we want is the density. So we are computing the gain matrix, which is this one. If we didn't use any smoothing, which is this term, then we would get some spurious peaks in the profiles. So we use the Tikhonov method with this this term in the gain matrix. You see that there is a parameter that we have to fine-tune, which is the smoothing parameter. So there are many ways to try to find the best smoothing parameter. I have tried a lot, well, the best method that I found was this one. So was to, in fact, use the smoothing error. So here you have the smoothing error. That's the averaging kernel minus the identity, and so this is in fact this curve in blue here. You have an increase of the smoothing error when the smoothing parameter increases. Because the averaging kernel are getting further away from the identity matrix. And you have also a decrease of the retrieval error, which is this term, which is here computed with the first moment method. While the smoothing error is an increasing function of the smoothing parameter, the retrieval error is a decreasing function of the smoothing parameters, and hopefully when you combine the two, you get a minimum. And this was the minimum for this case. So when you use a too small lambda parameter, in fact, you get those highly spurious peak in the profile. When you use a too high value, so this is the brownish curve that you see here. In fact, what is happening is that the profile is getting further away from what seems to be the variability of the profile. And the best parameter that was found here is 0.63, so that's the reddish curve that's passed here through. So that was it for the retrieval method. Here are finally some of the results. Here I'm just showing results that are already known, and just to show you that, well, with solar occultation we have a lot of variability in the latitude. So we are in fact scanning a lot of latitudes along solar longitudes very fast. And here you have mainly a result for Martian year 35 and Martian year 36. Martian year 35 and 36, in fact, in the second half year, had very similar latitudinal coverage, and you see here in the density that was retrieved very similar values as well. You see this increase of the density in the second half year. This is because, in fact, we are getting closer to perihelion, so there is a more intense incoming solar flux. So this is increasing the temperature at the surface. There are some small convective cells injecting dust into the atmosphere, which increase the temperature, and so the scale height increase, and you have an expansion of the atmosphere. So this was something that we were that we wanted to find here. So here you have some temperature profiles. Here is for the full mesosphere. What is striking, in fact, in those profiles is those warm layers that we see at very specific local times. It's always in the late morning that we see them. So I was having a look at those strong warm layers that we see in the mesosphere of Mars. And well, I define them as being a warm layer. So when you have some values which are 20 Kelvin higher than the background, and this happens for 14% of all profiles. Here you have the distribution of all those warm layers. So that's the orange dot, and the blue dots are all the occultations that was made. So you see that there are some biases in the distribution of the measurements. So we are less well scanning the equator. The local time are very related with latitudes, but we still see more of those in the morning. And in fact, those strong warm layers are also seen in models, but with a weaker amplitude. And from modelists, this is thought to be, in fact, a difference in the models. With this seems to be related with thermal tides, and the phase of the thermal tide seems to be not adjusted correctly with those that we see here. So yeah, those strong warm layers might be related with thermal tides. Here you have some histograms of the distribution of those strong warm layers. So again, we see them. In fact, I've split those histograms with half years. So you have Martian year 35 first half year, second half year, and Martian year 36 first half year. And we see them more often in the southern hemisphere in the first half year, and then more in the northern hemisphere in the second half year. There is no longitudinal trend here, but it's probably due to the fact that I'm smoothing, in fact, all values between a full half year. And we see, in fact, most of those strong warm layers that are appearing, in fact, in the morning. This is clear in those histograms here. So I was having a look at the possible thermal tides, non-migrating thermal tides. Here you have some sets of profiles that are very close in solar longitude, very close in local time and in latitude. And you see, in fact, more variability. In fact, when we have local time that are closer to between 7 and 9 o'clock. In fact, when I try to fit what seems to be non-migrating thermal tides, well, I get amplitudes of around 10% of the background temperature in the morning, around 5% in the afternoon, and around 0 around midnight. So that's all what I wanted to show about those strong warm layers. A last point is that if you want to change the planets you want to study, then I'm providing all the data. In fact, we in the NOMAD team are providing all the data that we are retrieving. So there are now 50,000 NOMAD profiles on this website, which is a website that gathers a lot of planetary atmosphere data. And there is now water, ozone, CO2 temperature, ozone, carbon monoxide. So please have a look if you are interested. And that's it. So yeah, this is mainly what I said during the presentation. So I will stop here. Thank you for your attention.